Hello, I'm Megan, and here you are applying for a software developer internship with Gator Nation. So let's start with a few questions. And the first one is, why do you think you would be a good fit for Gator Nation?
Well, first I'm going to start off just by introducing myself.
Mhm.
I'm Matthew, and being a software developer is something I've always wanted. Is my father's job, my father's father's job, father's
Interesting.
father's father's job. So I think ever since I was a child, I'd always been developing, making things, and software development is really this channel through which
Mhm.
I can push my creativity and allow myself to do what I want. So that's why I'd like to be a software developer.
Right, awesome. What do you think got you into software development?
Well, I think the many aspects of creating just things in general and
Mm.
how a lot of it is puzzle solving. So there are
Right.
things like debugging, as well as many things that you can do. I mean, there's so many languages to learn, so many
Mhm.
individual aspects to them. So I think just wanting to learn them all and seeing what I can create is what got me into software development.
Right, I think that got a lot of us into software development, seeing it as a
Mm.
puzzle and being able to be creative with yourself. And for the next question, how would you describe your strengths?
My strengths? Well, I think I do have several strengths. One of them is working on a team. I've completed several internships before, as well as worked in several group projects.
Mhm.
And so I'm familiar with how to be a team player as well as a leader. I know how to allocate work and organize team meetings and get things going when they're not necessarily going as well. When we run into any sort of any sort of stoppage, we just evaluate what's going wrong
Mhm.
and we ask ourselves, what can we do better here? So I think in terms of being a team player and being in a group, that's where I can really shine. Additionally, I think I'm also good at problem solving, so I can
Mhm.
seek things out on myself. I know where to look, but in the case where I do need help and I can't necessarily do everything by myself, I'm okay with asking questions and admitting that I don't know what's going on.
Right, that's perfect. I like that. And what about, tell me a time maybe where your weaknesses were shown and you decided to kind of overcome that. Maybe something that went wrong with the project, or somehow you wanted to help your teammates with something, anything of that sort.
Yes, well, this brings me back to, I guess, last summer we were training this machine learning model,
Mhm.
and it was a bit interesting, a bit difficult because I'd never done it before. So I was kind of in a rut. So I was
Mhm.
just really asking all my mentors, um, what can be improved here? How can I improve the accuracy? What's going wrong? Why isn't this giving me the correct output I want? As well as collaborating with my teammates and just trying out different things within our each other. So there was a lot of communication going on,
Right, right,
and through the end, we were able to come up with a good model
right.
with some high accuracy. So when things weren't going well, we just really tried to communicate and understand what was going wrong,
Mhm.
and we were able to get through the problem.
Right, right. I see the power of communication.
Yes.
And we will be going over that with a technical interview question as well. So I encourage you to try to ask as many questions as you can. And well, let's get started. All right, so let's get started with the technical interview question. And I'm going to start by giving you an array, and we are going to call it, let's just call it nums. And I'm just going to give you a set of numbers, so we can do -1, 0, 1, and we will do 2, -3, and then 2. And what I want you to do is return or give me the triplets in the array such that the sum of each number in the triplet that you find equals 0. So in this case, I would want you to return an example triplet is -1, 0, and 1, because each of these will add to equal 0.
Okay. And does each number have to have a distinct index in this array?
Yes, yes,
Okay,
you cannot
I see.
reuse an index.
Okay, um, I see. But I'm allowed to use the same number in like different triplets, right? So like if there was 1 in this triplet, but there was 1 that was also used in another triplet, I'm
Right,
allowed to use
yes.
Okay.
So
I
another
see.
one could be 1, 2, and -3.
I see. Okay. And is nums always going to have at least 3 integers in it?
Yes, you can
Okay.
assume so.
And it's always just going to have integers in it, right?
Yes.
Okay. I see. Yeah. So then the first solution that comes out to me then is the simple naive brute force solution where you just enumerate through each triplet, and if the sum of that triplet is equal to 0, then we just put that in the set, and then we return it. So I think first, in terms of time complexity, we're just going to assume that there are n numbers in this array. And then since we're going through each triplet, we're just doing n choose 3. And so that's just going to be, what is that, n minus 1, and then n minus 2 over 3 factorial. And then you can just rewrite that as of n cubed time complexity. So that's the first initial solution that I have. Would you like me to write it out in pseudocode now?
Yeah, sure, feel free.
All right. So I'm just going to create this method then, and it's going to return, let's say, an array, right? Array, and we're just going to call it get triplets. Triplets. And then it's going to take in nums. So this is it, and like I said, we're going to iterate through each triplet in here. So we're going to start our first array. Let's just say I is equal to 0, and then I less than, not less than or equal to, but just less than nums dot size. And then we're just going to increment I through 1. So let's just say I++ for that. And we're just going to repeat this, but now we're going to have another embedded for loop and then another one, just so we can keep track of these 3 distinct indices.
Right.
So I'm going to say, we're just going to say j this time. 0, j is less than nums dot size. And then we're of course going to increment j as well. And then one more time, and let's just call this index k. And we're initializing that to 0. And then k, oops, less than nums dot size. And then lastly, we're going to increment k at the end of each loop. So, like we said, first, the thing we don't want is the indices to be the same.
Right.
So we're going to check if either of these have the same indices, then we're just going to continue the for loop. So we can do this inside of here. So if I is equal to j, or I is equal to k, or yeah, and then or j is equal to k, equal to k, and that's all the comparisons we need to make, right? I, k, and then j, k. Yeah, so we're just making sure that none of these are the same. So if they are, then we're just going to continue the for loop, and we're not going to continue with the rest of the loop. Then what we're going to say is, if this sum is equal to 0, then we're going to add this to some like result of, let's just say, we're just going to call it some result vector, right? And so we're going to actually, before this loop, just declare this vector. So let's just say, let's call it an array. An array, and we're just going to call it result. and this is just going to be initialized to nothing. And then we're going to start this for loop. And then what we're going to want to say is if their numbers sum to 0, then, like we said, we're going to add it to result. If nums of I plus nums of j, and then plus nums of k, if that's equal to 0, then we're going to add that to result. So then result, let's just say add, and nums I nums j, and then nums k. Yeah. So within this for loop, now we're checking and we're adding these three numbers, let's say -1, 0, and 1.
Mm-hmm.
And we know that they don't have the same indices, so we're adding them. And another thing we have to worry about, so we're not allowed to have duplicate triplets, are we? So if there was like -1, 0, and 1, and then it was just repeated again, we would only repeat, or we would only return this once, right?
Right, so if I gave you something like -1, -1, and 2, and then we had that repeated, so we'll just do the same thing. You would only return one triplet being -1, -1, and 2.
I see. Okay. So now that we have that in there, we can continue with this, and we can iterate through result again and say, okay, if any of these are the same, then we're just going to remove that. So I think that's one way to continue. And like we said, yeah, that's one way to continue. But I think another way that would be much simpler and to keep this O of n cubed would be to just store these in a set. And so when we're adding them, that would just handle, okay, if this is already in here,
right,
then we're not going to continue to add it.
Mm-hmm.
So now that we know that there's no duplicates, I'm just going to let's just say that this is a set, right?
Mm-hmm.
Set. All right. It's time to switch colors. Okay. So we have the set, and now we're adding it. And then we're just going to assume that when we add it, it handles this, is it in there or not? And so at the end of this, we basically have these triples. Like we said, none of them share the same index, and they all add to 0. And now because it's a set, none of them are duplicates. So that should satisfy all the constraints. And like we said, there's always going to be 3. So we don't need to worry about this necessarily going out of bounds or anything like that. So yeah, we can just return at the end of this. And let's just assume that our programming language can just turn the set into an array. So let's just say array, and then result. And so I'm just going to go over this solution with this example that you've given me. So we start at the first indices, but then since we all set them equal to 0, we're just going to continue until they're all different. So we're going to start 0, 1, and 2.
Mm-hmm.
And then at that point, none of them are equal. So then we say, is -1 plus 1, or plus 0, plus 1 equal to 0? And we see that, okay, they are equal to 0. So then we add that to our set. Then we go through the next index k to -1 plus 0 plus 2 is not equal to 0. And then we find similar results for -3 and 2. And then we do the exact same for loop again, but now our j has moved. So -1, 0, and 1. That happens again because we initialize k to be 0. But then, because we're using a set, when we run into this triplet, we know that we've already added it. So yeah, so that basically just occurs again and again until we run into, what is it, 1, 2, and -3? Yeah. And we see 1, 2, -3, that's equal to 0. So then we add that. And then eventually, again, we're going to run into 1, -3, and 2. We see that that's equal to 0, but because we're using a set, we know that this triplet is already in our result. So it seems as if this solution should work for filtering out the duplicates and making sure that these triplets equal to 0 and don't have the same indices.
Right,
I
right.
think it should be correct.
Right, that's perfect. All right, so if I were to ask you about maybe a minor optimization that you could do you think you could think of one, maybe?
Yeah, I think so. So in terms of space complexity as well, I just want to, let me just, before I get into any optimizations, let's just say time. This is O of n cubed. And then for space, let's just say O of n, since we have this set of results.
Right.
So yeah, if we ever wanted to improve this, I think we would want to go for this time complexity here, since here we're just naively checking for every single enumeration of triplets. Yeah, so I think this might be able to be brought down to O of n squared if we looked at every pair of indices. So for example, -3 and 2, they add up to 1, or -1. And since we want -1 plus 1 equal to 0, because we want a triplet of 0, we would want to check through this nums array and see, is there a 1 in here? And if there is, then perfect. So through that, we can kind of predict what we need. So like, let's say -1 and 0, those add up to -1. We take the negation of that, which is 1, and we say, okay, 1 is in here as well. So I think we can kind of build off that idea to only enumerate through pairs of numbers instead of the triplets, and that would just be reduced to O of n squared now. So that's the idea I'm getting from it. Would you like me to write it down?
Sure, yeah.
All right. All right. And then another part of the optimization that I want to mention is sorting. So let's take this array, and let's just say we want to sort it right. So we have -3, and then -1, and then 0, and then 1, and then 2, and 2. Yeah. So what we can take away from this now is we can look at both of these ends, -3 and -2. And then we can also just, let's say, sort through this array first. Or not sort through this array, I'm sorry, iterate through the array. So -3. To find a triplet that equals to 0, we want to find a pair that equals 3. So bouncing off the idea that I said earlier to find pairs first, we can iterate through this array once to find a pair that equals to 3. So we can start at this index here first, and then this one right here. So there are 3 cases, -1 and 2. This is one of the cases where 1 is actually less than 3. So since 1 is less than 3, and we know that this is sorted, all we need to do is increment this left array to go here now. And we know that 0 plus 2 is larger than the previous sum, but still not equal to 3. So we continue again with the same case. We increment the left index, and now we see 2 and 1 both equal to 3, and we've found a triplet, -3, 1, and 2, which equals to 0. And then we would add that to whatever set that we had previously. And so there's the other case as well, where the sum isn't less and it's not equal, but it's greater. So in that case, we would actually increment, or we would decrement the right index to try and get a lesser sum so that we can match again. And yeah, once we find a pair, we also just continue as well until the left and right indices meet, just to find all possible pairs that add up to 3. So that's the gist I have of this optimized solution. First we sort, then we iterate through each element, and for each element we do this O of n time operation to find a pair that sums to that negation of the number. And then once we do that, we add that to the set. And so since we're doing an O of n operation for each iteration, that becomes O of n squared. And then the space as well, it stays the same. And yeah, so that's I think the gist of it. So would you like me to write it down?
Let's see. So the one thing I wanted to ask before possibly writing it down is, how do you think using the sort function could possibly make our solution faster compared to not using it?
Okay, well, I think the sort function allows us to better check for this pair. So for example, if we just left this unsorted, we had -1, and we wanted to find a pair that summed to 1. We would have to iterate through each pair here, right? Our same trick of starting at the ends and then decrementing and incrementing the indices based on how they compare to this negation, it's not going to work because we don't necessarily know if it's sorted. So what we would have to do is this O of n squared operation, where we find every single pair. And from there, that would essentially just become in the same class of our last solution, where it's O of n cubed, since we're iterating through each triplet. And so sorting allows us to better check for the pair, and it becomes an O of n squared solution rather than O of n cubed.
Right, right. Yeah, for this solution, you couldn't get better than n squared, so this is great.
Okay. So would you like me to write it out now?
Right, yeah, sure.
Okay. So I'm just going to erase this little thing here so I can have more space to write.
And for this, you don't have to write anything large, like a block of code.
Okay. So yeah, the first thing that I'm going to do is just, let's say we have the sorting function. So just sort, and then nums. So now we know that nums is sorted. And then, like we said, we're going to iterate through each integer in nums. So I is 0, I is less than nums dot size, and then increment I. And then, like we said, now we're going to keep these 2 pointers at the ends of the array. So we're going to have, let's just say 4, and we're going to have this left one, let's call this left, at 0, and then right, and then let's just assume that n minus 1 is the last index. And so yeah, we're just going to keep doing this until left is greater than or equal to the right. Yeah, and so that's our loop, and we're going to change these indices based off of the result compared to the negation. And so actually, in between here, what we're going to want is to calculate the negation, like we said. So yeah, I'll just rewrite this. Okay, so like we said, we want 1, but we have -1. So let's just call this want, or let's just say need, right? So need is equal to negative of nums I. And then we're going to find a pair in this sorted nums that is equal to need. So what we're going to do is have this loop again, and let's just say left is equal to 0 and right is equal to n minus 1. And then what we're going to want to do is just say while left is less than right. Okay, now we're going to do this while loop, and we're going to compute the sum. So their sum is just nums left plus nums right. And when we do that, we're also going to want to be conscious that none of these share the same index as I. So we should probably, do this before the sum, but it actually doesn't really matter. So we're just going to say if left is equal to I or right is equal to I, then we're just going to, we're going to want to, well, actually, it'll depend. If left is equal to I, then we're going to increment left. And if right is equal to I, then we're going to want to decrement I, or right. So if left is equal to I, then we're going to say left is, let's just say minus equal to 1, so it subtracts 1 from itself. And then we're going to continue this, or I'm sorry, not left, add. And then we're going to continue, and then if right is equal to I, then we're going to say decrement equal to 1, and then we're going to continue. So now this makes sure that all the indices are distinct, and now we can kind of just tweak this left and right based off of how the sum compares to our need. So I think, I'll just continue to write this. Okay, so like we said, first, if sum is equal to need, then we're going to add that to our results. So if sum is equal to need, perfect, we have this triplet. So we're going to add that to, let's just say we have this result here. And it'll act in the same way in our previous solution where it's a set. So it'll take care of the duplicates. Let's just say nums, which one was it? Yes, I, and then nums of the left, and then nums right. And we know that these are all distinct because left is always going to be left and right. And if they are ever equal to I, then we change the indices. So these are always going to be distinct, and the result will always have distinct pairs as well. Now we need to handle the case if the sum is less than the need, then we need to get a larger sum. So we're going to increment left. So left plus equal and we're just going to say else if. And then same thing again, else if, well, we don't have to say else in this situation. If it's not less than or equal to, then it's got to be greater. So we can just kind of simplify this and just say else. And then we're going to say decrement right, because the sum is too large, and we're going to want to go towards a smaller integer. So right, we're going to decrement. Yeah. And that should be it. And then at the end, like we said, we have our results, and we're just going to return that result.
Right, our assumed result.
Yeah. So I think I'm just going to try it again now with this. We're going to have the nums, and the first thing we're going to want to do is sort it. So -1, -1, and so that's there just 4 times. And then we have 2 and 2, 2 and 2. And now we're going to iterate through each integer in here. So -1, and what we want is 1. So we're at this one first. And we have the left at 0, and then the right at n-1. And then the first thing we calculate the nums, but then we go through this, and we see that the left index here is actually equal to I. So then we increment, because we don't want the same index. So we do that again. And then we see the left and the right are not equal to our starting index. And then we see -1 plus 2 is equal to 1, which is what we wanted. So we add that to our results. So now we have -1, -1, and 2 in terms of our current solution, our current result. And then we do that again. We iterate. Actually, yeah, now that I see this, I have discovered a bug. So if we ever do find the sum that matches the need, we're just going to have this infinite loop. So what we should add here is something that increments the left and decrements the right, so we can continue to find it. I don't have space, but if I did, that's what I would add. So assuming we did have that, we would continue, and we would decrement I, or the right index, and we would increment the left index. And we would again find 2 and -1. Those both add up to 1, which is our need. But because we have a set, we recognize here that this is already in there, so it's not added again. And then we do the same thing here, same pair, same thing, it's already in there, so we don't. And then we increment I again, and we essentially go through the exact same process. So at the end of it, I don't think there are any other triplets in here, so this should just become the entire result, which is returned. And so yeah, I think another thing that I've also realized is that in terms of space complexity, I think the worst case is O of n cubed, right? Since we're going through every triplet, or at least in the first case, we went through every triplet. And the worst case is that every single triplet is distinct and adds up to 0. So I think that was a tiny modification. But it becomes O of n squared in terms of time, and the space essentially just stays the same.
Right, right. Okay, so we went from O of n cubed and we optimized, especially using the sort function, which was very helpful, and went from O of n cubed to O of n squared. That was great. Okay, and we went through a test case as well. Awesome.
Awesome. So is that all for the question?
Yes.
Awesome. So I get the job?
Yeah.
Okay. Awesome.